Hi there. In this video, I will talk about 3 most underrated concepts. First, let me give you some background. My name is Hunar. I have spent years studying the human brain. I used to tell my friends the human brain is the most complex system in the entire multiverse. As a neuroscientist, I was taking pride in saying that. One day, someone told me that's nonsense. You don't even know what complexity is. So I started to read about complexity to prove I was right, but I fell into the rabbit hole of chaos theory and the world of fractals. It was then I realized my understanding of complexity was upside down. It was like waking up to a new reality. I was shocked to learn that our brain is not the most complex system. It doesn't even beat pi in the complexity department. Another shock was I learned that complexity is easy to generate. For example, here are 2 particles attracted to each other by a simple attracting force. Make them 3 and we have the famous 3-body problem. Make them 4 and we have unspeakable complexity. Increase the number and the type of the particles and we will see many unpredictable shapes keep popping up like this bug flying around. You can produce an immense amount of diversity and complexity with simple rules. What is more shocking is that complex new shapes will continue to emerge even if you set the parameters randomly without any fine-tuning. The point is, complexity is easy to generate. But why does that matter? Debaters often ask, how did all this complexity come about? For me, this question has lost its intrigue. The real question is, if complexity is so easy to generate, why can't we do whatever we want? Why this life still feels like a struggle? And if our brain is not the most complex system, how does consciousness arise? So I have been thinking and thinking again and again, and I have concluded that these 3 principles can explain everything. I call them the principles of reality because when you grasp them, you will see them everywhere. No matter where you go, whatever happens, you will see these principles are behind it. Suddenly, 2 of these principles are about limitations. I had an existential crisis with the second one. I was like, science is doomed. Luckily, the third principle is optimistic and offers a partial solution. If you are ready to learn about these principles, take the red pill and stay with me till the end. The first one is the principle of locality. Stephen Wolfram calls it computational boundedness, but locality is more mainstream. As observers, we can only process the nearby information. Our viewpoint on reality is very limited, both in time and space, because there is a maximum speed limit. Nothing can exchange information faster than light. This means distant objects can't interact without a delay. And because we are part of this same reality, we are bound by these limitations too. We always have to make decisions without seeing the whole picture. Imagine your goal is to find the highest point here. You say, oh, this is easy. According to the evidence, I should move to the right. So you do, and you reach the peak. You think you are on the highest point. But if you see the whole picture, you realize you are stuck on a local maximum. This limitation applies to the time window too. Let's say Bob kills 3 people and Alex saves 3. You say, oh, if I prevent Bob from living and breathing, this world will be a better place. But Dr. Manhattan says you are wrong. He can see the future and tells you that in future Bob's son will cure cancer and save many lives, while Alex's son will kill many lives. The point is, in the grand scheme, we are horribly underinformed. So how can we ever make a good decision? The short answer is follow the local evidence, but be open-minded. In fact, most advanced AIs today are trained by gradually following the local evidence. In a previous video, we used simulation to show that we can reach the global maxima using 2 groups of people, conservatives following the local evidence, while liberals exploring around. However, that approach required too many trials and errors and cost many lives. I want to find a struggle-free optimal path, but for that we need to predict the future. For example, Dr. Manhattan plays the knight here. You may think it's a bad move because the bishop can capture it, but Dr. Manhattan already knows that black will blunder and move the rook instead, leading to checkmate in 2 moves. The point is, we need to predict the future to make optimal choices. Science is all about making predictions. Remember in high school, we learned to predict where a star moves or where a ball lands using Newton's equations. Many scientists are hoping to discover the theory of everything, which is an equation that explains all the forces in our reality. If they find that equation, they will understand how our universe works, and they will be able to predict everything, fix everything, and we will end up living in a utopia. Well, that's what I believed a few years ago. But one day, I was trying to train a neural network to predict the Mandelbrot set. I thought this would be easy because Mandelbrot has a lot of regularities, but I quickly realized this task is impossible. Even with a large neural network, it could never replicate the endless details of the Mandelbrot. I was baffled. How come a simple rule with few lines of code can generate an endless amount of emergent patterns, while a neural network with million parameters can't simulate that? Looking for answers, I came across a decade-old video by Wolfram. He pointed to these triangular shapes called cellular automata. To paraphrase, he said, this is rule 30. If you apply it for a few steps, it will produce this pattern. Can you predict what happens at time step 100 just from the rule? The answer was no. You have to calculate all the intermediate steps leading to it. He even put a price for that. He called it the computational irreducibility principle. I thought, wait a minute, this is similar to what I face. The second principle is very sad. It puts a big limitation on science. I really hoped that one day it would be disproved, but then I came across Gödel's incompleteness theorem and the halting problem. They too place limits on what we can ever hope to achieve with science. You see, I told you complexity is easy to generate, but I didn't say it's easy to understand. This may sound counterintuitive because we usually think that if something is hard to understand, it should be hard to generate too. But that's not the case with complexity. So what's understanding? Let's say we have two systems, system 1 and system 2. If system 1 can predict the behavior of system 2, we say system 1 understands system 2. And if system 1 can simulate system 2 with less computational power, we say system 2 is reducible. System 1 is analogous to our brain, while system 2 represents the world that we are trying to understand. To examine reducibility, Wolfram used cellular automata, which are simple rule sets where each cell can be in one of two states, black or white, determined by the state of its neighboring cells. If you apply this rule for 20 steps, it will produce this pattern. You can set the initial cells randomly and watch how the rule progresses. Wolfram systematically explored all the rule sets in elementary cellular automata, and he found a sharp division between what the rules can produce. Rules that produce reducible complexity. These rules will quickly drop into repetition and are very predictable. If you are asked to complete them, it will be very easy to extrapolate. On the other hand, rules that produce irreducible complexity are chaotic and unpredictable. They are very hard to extrapolate and predict. A similar comparison can be made between rational and irrational numbers. When you calculate rational numbers, they quickly fall into repetition, while irrational numbers never repeat and continue producing new patterns. So why this is important for our quest? Let's say we have two one-dimensional universes. In the reducible universe, our scientist observes the following events. He observes 2 followed by 5, then 8, 11, 14, 17, and so on. The clever scientists say, oh, I got it. Our universe operates according to this 3 multiplied by time minus 1. Then someone asks, what will happen in the future at time 100? The scientists say, easy, just plug in 100 for time and we get 299. This universe has a happy ending because they know what will happen to them even before it happens, and they can rest in peace. In the meantime, the scientist in the irreducible universe observes the following events: 1 followed by 2, then 3, 6, 9, 18, 27, and so on. He says, oh, our universe operates according to this rule. So to predict the next step, multiply the current state by the previous state and divide them by the state before that. Easy peasy. But then someone asks, what will happen in the future at time 100? The scientist says, wait, we don't have time in our equation. I cannot even tell you what happens at time 10 without calculating the previous states. To tell you what happens at time 100, I have to calculate all the states leading up to it one by one. Now, because the scientist can't calculate the rule faster than the universe he lives in, this universe can never know what happens next, and that's why they can never rest in peace. This is true for our universe as well. If we want to know what will happen to us in the next hour, even if we know the theory of everything and have the exact state of all the atoms in the universe stored in a hard drive, when our computer is done calculating, it will only spit out the next state of our universe, which is the next picosecond or whatever the smallest time update is. So we have to put the new state back into the computer again and repeat the process for gazillion times before we can find out what will happen in the next 1 hour. And because we can't run the simulation faster than the universe itself, we can never know what happens in the future. We have no choice but to live through the present. This is problematic because we said to make optimal life choices, we have to predict the future. But now we are saying to predict the future, we have to live a life first. What kind of paradox is that? You may think if we had access to a supercomputer that runs faster than our universe, the problem would be solved. But I don't think so. Let's say you find a magic lamp and ask the genie for a supercomputer that runs 1000 times faster than our universe. The genie grants your wish and you load the current state of the universe. The simulation starts. You zoom to Earth, then zoom to yourself. To avoid the problem of infinite regress and paradoxes, let's assume the simulation doesn't include the part where you found the magic lamp. So the simulation predicts what will happen to you if you hadn't found the magic lamp. In the simulation, you receive a call from your friend. He asks you to come to his birthday party. After the phone, you head out and cycle to your friend's house. When you arrive and join in, one guy shouts, "Hey dude, bring me that glass of water." You seem a bit reluctant, but then you bring him the glass anyway. After the party, you come across two rooms. You choose room A, but when you enter, two guys are fighting. One of them shoots a bullet toward the other, but the bullet hits you by accident. Your life is over and the simulation ends. At that moment, back in real life, your phone rings. When you answer, it's your friend asking you to come to the party. At first, you think about not going to the party, but then you say, I'm not going to room A and I will be safe. So you cycle to the party, you join, the guy shouts, "Hey dude, bring me that glass of water." You think about rejecting the request, but you will do it anyway because you don't want to create a non-simulated branch yet. After the party, you come across the two rooms, but this time you avoid room A and decide to enter room B. Luckily, room B is safe, but from this point on, you don't know what will happen next, so you need to go back to the supercomputer. Making alternative choices after each simulation is compatible with a deterministic world, because we are examining two different universes. In the simulated universe, you don't have access to the supercomputer, but in the real universe, you do. Everything else is identical between the two universes. It's like a controlled scientific experiment where you change only one variable to see what happens. In this case, that extra knowledge led you to a better outcome. So it seems like the supercomputer could help you live an optimal life. Every time you mess up in the simulation, you can choose a better path in the real universe. However, there are two problems with this approach. First, from now on, you are more likely to put yourself in dangerous situations, and at some point you will be trapped in a place where all the outgoing paths lead to bad outcomes. This happens because of the locality problem. Your choices are still based on local evidence. The supercomputer expands your view, but it doesn't make you a global observer. You still don't know what might have happened if you hadn't gone to the party in the first place, or if you hadn't brought that glass of water. There are countless other branches you have overlooked. Any of them might have led to a more optimal outcome. One solution is to use breadth-first search. Here you explore all the possible branches before going any deeper, then explore all the sub-branches. However, this approach grows exponentially. and eventually even your supercomputer won't be able to handle it. Even if you gain access to a more powerful supercomputer, you will just become a watcher because you need to watch infinite branches of your life before you can pinpoint the global optimum path and decide to relive it. But there is even a bigger problem. You are mistaken if you think you can enjoy reliving what you have already watched and memorized. Most of the joy and excitement we get from life is from living through uncertainty and exploring novel paths. So I would argue that you would just sleepwalk your already watched paths. We know from many neuroscientific studies, including one of our studies, that our brain is more active when we encounter novel and unexpected events, but less active when we encounter a repeated event. When something is repeated and become predictable, we get sleepy. When something is totally random, we lose interest, but we are at the peak of excitement when our expectations are about to be either confirmed or violated. This is because searching and thinking are only meaningful if you have a goal but not sure which path will take you to the goal. If you are 100% sure which path will take you to the goal, then searching and thinking become unnecessary. On the other hand, if you have no goal or the goal is impossible, then searching and thinking are pointless. And because thinking is important for existence, we can conclude that only the middle one deserves to be conscious. The long story short, it doesn't make sense to relive the already memorized path. So you have to decide whether to become just a watcher or be brave enough and live through uncertainty. It seems like we all chose the latter. Honestly, I don't remember making that choice, but here I am, at a point in space-time where most of the outgoing branches lead to failure. I might have a slight chance in some branches. It would be great if I could copy myself many times, then mutate the copies to take different paths. But wait a minute, DNA has already been doing that for billions of years. Through evolution, it has sent copies everywhere. Just on Earth for now. Back when we were bacteria, we had the superpower to make many copies of ourselves in a short time. But in human form, copying is much more difficult. If you ask a neural cell to make a copy of you, it will say, no, I can't, I am only specialized to think. If you ask the heart cells, they will say, no, we can't, we are too busy pumping blood. But if you ask gonads, they will say yes, but they have to duplicate many times to form all the human cells, then specialize again, and that requires 9 months. Even after that, it takes another 18 years to become ready. So by the time we make a fully functional copies of ourselves, bacteria have made countless copies of themselves. We are going to lose the survival game unless we choose the paths wisely. Luckily, we have memory. Some paths do repeat, and when we remember them, we don't have to relive them again. We have evolved the ability to sense pain. Pain notifications alert us about the immediate dangers. We can eliminate those dangerous paths right away. The problem is, we will still miss the long-term dangers, and by the time we become aware of them, it's too late. We need to predict these long-term dangers before taking these paths. Luckily, our neocortex has the superpower to do that. From now on, I'm going to say our brain is the best prediction machine in the entire multiverse. I mean, on Earth. You may say, Gunnar, didn't you tell us we can predict future? Well, yes, but didn't I tell you there is hope? So far, we have been talking about making 100% accurate prediction. But if you relax your requirement, life will become much easier. In fact, you only need to be more accurate than your competition. Being more accurate doesn't apply to bacteria because they multiply very fast. It only applies to those who can't make enough copies in time. So how can we make predictions in a computationally irreducible world? Predictive abstraction is the answer to these limitations. Abstraction is a well-known concept in category theory. It's all about reducing complexity by focusing on the main ideas and ignoring specific details. So let's say you have Bob, Ali, Joe, John, etc. And you have Bob's car, Ali's car, and so on. To apply abstraction here, you would just call everyone on the site a person and everything on the side a car. In this case, we group them based on similarity, but we can use simpler criteria like coarse graining, where we group things based on their proximity to each other. Markov blankets are another way to abstract information. When a stable membrane separates the inside from the outside, We can treat the entire system as one entity. Multivariable linear regression is another way to abstract information. It's a more sophisticated version of coarse graining. In coarse graining, we simply average the nearby variables, but in multivariable regression, we do a weighted sum of the variables. Most of the modern science relies on regression analysis. Finally, multilayered neural networks are currently our most sophisticated tool for abstraction. They are used in many AI models nowadays, and our brain uses a biological version of neural networks consisting of billions of neurons. Let's start with coarse graining because it's very simple to do. All you need is a low-resolution sensor with a low sample rate. Here is Mona Lisa coarse grain. Here is more coarse graining. So how does that help with prediction? Let's revisit our particle simulation where we formed a bug-like shape from 100 colored particles interacting with each other according to the following rules. Now, if a frog wants to catch the bug, it needs to predict the bug's next move. But due to the computational irreducibility principle, the frog's brain can never simulate 600 particles faster than the system itself. However, if the frog senses the environment with a lower sample rate, its brain now only deals with 70 coarse-grained particles, which is much lower. Now it's possible for the frog to simulate them faster and predict the bug's next move. One thing to note is that coarse-grained simulations may not exactly match the original, but as long as they are accurate enough for the frog to catch its food, that's what matters. Don't underestimate the power of coarse graining. It's used everywhere in science, in chemistry, in physics, under the name of effective theories. In fact, most of what we sense or measure is coarse-grained to some degree. Markov blankets are another way to do abstractions. Let's say we have a network of nodes causally connected to each other. If you want to predict the state of node X, you don't need to know the current state of all the nodes. All you need is the state of its Markov blanket, which include its parent nodes, children nodes, and partner nodes. The effects of all the other nodes are encapsulated by the Markov blanket. However, there is a catch. To know the state of the nodes in the Markov blanket, you also need to know the state of their blankets, which eventually include all the nodes in the system, defeating its purpose. Luckily, most real-world systems are sparsely connected, where nearby nodes are more connected to each other than to distant nodes. This makes it easier to identify groups of nodes separated by stable Markov blankets. The reason for this sparse connection, in my opinion, is that forces in nature vary in strength and range. Just like in our particle simulation, when we simulated variable force ranges for different colors, we observed that nearby particles organized into stable formations demarcated by clear membranes. What's interesting is that the survival of the fittest is already in play, even though we didn't explicitly write any fitness functions into the simulation. This raises the question, what values can we measure to learn about the state of evolution in this system? At the beginning of the simulation, particles are dispersed throughout and have high entropy. For limited observers like us, there is high uncertainty about which path this particle will take, for example, because it's being attracted by all the other forces in the system, and we cannot compute all of them. However, as the simulation progresses, most nearby particles aggregate to form larger attracting forces, but in fewer places. As observers, we can now meaningfully coarse-grain this system into just 4 attracting forces. Therefore, we can predict with higher confidence where this particle will land as they move from a high energy state to a lower energy state. In thermodynamics, these state changes are captured by Gibbs free energy equation, which relates energy to entropy. Generally, entropy tends to increase or remain constant over time. However, for self-organizing particles, local entropy decreases over time due to the nearby attracting forces, pulling the moving particles for a settlement. Karl Friston, a renowned neuroscientist, generalizes the free energy principle to all living beings. He proposes that just like self-organizing particles minimize the free energy, living beings also minimize the prediction error. He uses a series of equations and concepts to show that these two worlds are connected and they all operate under the same unified objective, which is minimizing the free energy. Living beings are trying to minimize two quantities: the gap between their prediction and the ground truth, and the uncertainty in their prediction. In layman's terms, if someone asks you what will happen next and you reply it could be this or this or this or this, then you shouldn't be proud if you guess the answer, because what's the point of being right if you are so unsure? If you confidently say it's either this or this, but the correct answer is very far from your guesses, this is also bad, because what's the point of being confident if you are so wrong? According to active inference, you can minimize your prediction error in two ways: either by updating your beliefs to match the world, or by changing the world to match your beliefs. In other way, either you learn from the world so that you adapt to it, or you teach the world so that they adapt to you. The balance between top-down and bottom-up is crucial, because overusing top-down without listening to the bottom-up may lead to delusions or fascism. This may seem appealing because if everyone follows one order, everything becomes predictable in the short term. However, you will be trapped on a local maximum and lose the ability to adapt to a changing world. Remember, we share this world with many other living beings that are beyond our control, and one day we might even face aliens. Everything changes in the long term, so it doesn't make sense to trap ourselves at a local maximum and lose the agility to learn and change. That's why we have curiosity and a thirst to learn new things. Learning from the environment is present even in the smallest entities with Markov Blankets. Just like a neural network, Markov Blankets have sensory nodes, internal nodes, and active nodes. Nested levels of Markov Blankets functions like a deep neural network, where each layer progressively abstracts the information. So this reality has been coarse-grained and abstracted progressively, starting from the simplest cells all the way up, long before our brain even come into play. If our world were fully connected, it would be impossible for our locally aware brain to make any sense of it, because any event happening here would immediately affect everywhere. The limitations of our brain are matched by a sparsely connected universe where it can be coarse-grained meaningfully. This makes it possible to abstract the information at each level, and the interplay between the bottom-up and the top-down will make the long-term predictions possible. To give a concrete example, let's say Bob is a law-abiding citizen. Every day he wakes up at the same time, goes to his office, where he types the same email responses and answers the same questions. In the evening, he goes back home tired and then sleeps. In the short term, Bob's life is very predictable and stable in the short term, but in the long term, anything could happen, like Bob being hit by a car. These unexpected events are not predictable at this level, but on a higher level, the Ministry of Transportation can monitor these events by grouping Bob with other people and grouping cars under one category. This abstraction makes statistics possible because now they can monitor the relations among various categories, and this might reveal statistically predictable patterns. For example, they may find significantly higher accident rates on this road. Now they can build a bridge on this road and then accident rates will fall. This means at the lower level, Bob or whoever his replacement can now live a more predictable life without being hit by a car. This hierarchical level of abstraction and interplay eventually makes the inner levels more stable. Reducing surprise is essentially the same as reducing errors recursively, which we have covered in detail in a previous video. Before we conclude the video, let's put what we have learned into a small coding project. So open your Python editor, import NumPy and Matplotlib. Define a rule. Let's pick rule 30. Use Python dictionary to define the states of our rule. Define the number of steps and the size of a grid and fill it with zeros. Set the midpoint of the upper row to 1. Now apply the rule we defined to 3 neighboring cells and put the result in the next row. Repeat this for the entire grid and see how the rule evolves from this simple initial setting. Visualize the result and press run. Now examine the generated pattern and zoom in to the middle part. You will notice that the middle section is quite random and very hard to predict. You need at least 3 inputs to predict what comes at time 1 uniquely. and you need at least 5 inputs to predict what comes at time 2. Here, for example, to predict what comes at time 2, you need to apply the rule 4 times as shown here. You can skip the intermediate step at time 1, but if you memorize the input rows and their associated outputs, you can directly predict time step 2, but that will increase the memory requirement, and it's only useful for some patterns that repeat more frequently. If you look at the following rules, you notice their output is 0 regardless of the body of the third neighbor. Likewise, these 2 rules, their output is always 1 regardless of their third neighbor. This means for some patterns like this one, you only need to apply the rule twice, because now you have the complete information to infer the output without any further processing. There are 4 patterns like that where you can achieve 100% accuracy. But the remaining patterns, you can only achieve 50% accuracy. So if you use a simple neural network to learn from 4 inputs, we can achieve a total accuracy of 62%. Let's define a simple neural network. Define the inputs as x's and the outputs as y's, which is the middle part of rule 30. Define the network structure and the weights. Define a sigmoid activation function for the output, because we want the output to be between 0 and 1. Train the network. First do the feed-forward pass, then compare the output with the actual labels. Use the error to calculate the gradients, and use the gradients to update the weights. After training is done, you can see it's able to predict 2 steps ahead with 62% accuracy. And that's above the chance level. This is important because in a competitive world like ours, where we are computationally limited, both efficiency and accuracy matter. The objective is to maximize both. This is similar to the free energy principle, where the objective is to minimize both the model complexity and surprise. So if the red line here is your true future, you don't want your mental model to look like this. It's very inefficient. And you don't want it to look like this. It is very inaccurate. This one is better. Ideally, we want a perfect match, but due to the limitations, we will always have a degree of uncertainty. And that's what makes life interesting, and probably what makes us conscious. In conclusion, from the first principle, we learned that life is a struggle. We can't navigate life without trials and errors. From the second principle, we learned that if we haven't memorized a path, there is no shortcut to the outcome. We have to live through all its moments. From the third principle, we learned that we are now in a prediction game under a unified objective. It is possible that our future is already determined, but it is determined by the optimality of our choices. And the optimality of our choices is determined by how correctly we can predict the future. Thanks a lot for watching.